In this video we're going to show our first attempt at solving the acceleration of a box on an inclined plane. If you notice in the question it says there's no friction. We'll work on problems with friction next, but we're going to start with one without friction. And so in this case, to start with, we have the ramp that is at a 35-degree angle and an 85 kilogram mass. The only force that we can draw acting right now on the box is the force due to gravity. So the force due to gravity is pointed straight down, and so let's draw the force due to gravity vector straight down. I like to draw it going all the way across even the bottom of the ramp to make it easier to see things later. So we have that force right now, but as you can tell, the box will not accelerate downward due to gravity because the ramp is at that angle. So the actual direction that the box wants to slide is this way. And so what we need to do is let's draw another coordinate system. Let's draw our x's and y's. Instead of vertical as usual, let's go ahead and draw us a y, x and y coordinate system that is parallel to the surface of the ramp. And so that will make it a little easier for us to do the math, since that's the direction that the box will be moving down the inclined plane. So now we have a new coordinate system. We have the force due to gravity straight downward. What we would like to do is now split the gravitational force into x and y components. And so this force due to gravity right here is going to actually be the hypotenuse of the new triangle that we draw. So what we would like to do is have then the part of the gravity that is in the y component would be this direction, and then the x component would be this direction. It's really important to get this triangle drawn correctly. What the biggest mistake people do here is to make the y come down here and then the x do this. This bottom part right as it is right now, that is not the x component. That it has to be parallel with the x-axis up here. So when we draw our x, it has to be parallel. This has to be parallel with the x. So be careful when you're drawing the triangle to make sure that the y is on the y-axis, and then the x component will be exactly parallel to the x-axis that we've drawn. So now then we have this x component and the y component of the gravity. And I guess first we need to go ahead and figure out just what is the force due to gravity. So of course, to do that we just take our 85 kilograms times 9.81. If you need to pause the video at any time while working out, go ahead and do that, but I've worked it out ahead of time, and so I know this number is 833.85 newtons. That is the force that's straight downwards due to gravity. So we know the 833.85 newtons is straight downward. What we need to know now is, of that 833.85, what is the x and the y component? So we have the hypotenuse of the triangle. We want to know the two sides. We have to know an angle. The only angle given in the problem was the 35 degrees down here. And there's probably several ways that we could work the geometry on this, but I think the simplest way is to know that if this angle is 35, then we know that this angle right here is 55, and then since between the surface and this is a 90, then we know that this angle inside here also has to be 35. So if you need more help with that, then we can talk about it in class, but basically if you know this is 35, then if you have your triangle drawn as we did correctly, then it's going to be the same angle for this interior part of the triangle up here. It's going to be the same 35 degrees or whatever the angle on the ramp was. So now we have that interior angle of 35. We have the hypotenuse of the triangle. This is, we made this by definition a 90-degree triangle because we did the x and y components. And so now we can just use our basic trig functions to find what x and y are going to be. So for the first one, if we're trying to solve we're trying to solve for the x component, it's opposite of the 35 degrees, so we would use the sine. We would say the sine of 35 is equal to x over the hypotenuse, which is 833.85 newtons. And so plug that in your calculator, you multiply sine of 35 times the 833.85, and you would come up with 478.3 newtons. So that's what the x component is, 478.3. That is the part of gravity that's wanting to push the inclined plane down the ramp. To solve for the y, how much of that force of gravity is pushing into the ramp, then we would use the cosine, because the y is adjacent to the 35 degrees. So we would say the cosine of 35 equals y over 833.85. And when we solve for y, we would end up with 683 newtons. So the y is 683 newtons. So what we've done is taken the force of gravity of 833 and split that and say we can pretend like it's two separate forces of 478 and 683 and look at those individually. So this 683 is pushing into the inclined plane, but there is a force that is keeping it from accelerating that way. It is the normal force. So the normal force is pointed straight upward, and the normal force would be 683 newtons. If we were dealing with friction, we would need to use that 683 newtons to solve for the force of friction. But in this case, since there is no friction, then we can those two forces are balanced out and won't affect our net force. So the only force that is unbalanced, the one that's not countered by anything else, is the force of the x component, which is 478.3. So it's as if we're picturing then we have this one force of 478.3 newtons. That force, there's nothing counter it. There's no friction opposing it going the opposite direction in this case. And so the net force is 478.3 newtons. So to solve our final step to get the answer to this question, we know that the net force is equal to the mass times the acceleration. The net force is 478.3 newtons. The mass is 85 kilograms. And so we can solve for the acceleration then. We just take the 478.3 divided by 85, and we would come up with an answer for the acceleration of 5.63 meters per second squared. That would be our final answer. So that's the first step. In following problems, we will add friction to the situation, so that means we would have to use the normal force to calculate the force of friction and then find the net force. So we'll do that in following problems.